For the third part of Unit 6, that I think is another really important concept in terms of engineering as well as just kind of practical skills that I think a lot of you may find useful at some point during your lives, is the concept of reverse engineering and how to go ahead and analyze the functions of an object. Okay? Whether it's something that you have an idea what it is or what it isn't, there are a lot of reasons that reverse engineering is a key concept and kind of its own form of engineering. So the technical definition of it is reverse engineering is a process for taking something apart, analyzing how it works in detail, and there's usually an intention of being able to understand its functions, its structure, its operations, and then using that knowledge to go ahead and apply it. So there are several reasons why you want to look at reverse engineering. Part of it is documentation, part of it is discovery and getting a better concept of what is going on in the world. We can use it for investigation, seeing what went wrong, and we can use it to make product improvements. So, documentation. Okay, probably this is the most fundamental reason for having reverse engineering, and that's for whether you know that documentation has disappeared. Maybe it's an older item, 50 years old, 100 years old, where the documentation is no longer available, or you've got cases where it is available, but only to people that pay for that license. We can also use it to go ahead and make sure that things are interoperable. Just because it works for one system doesn't necessarily mean that it works for another. Computer compatibility could be an example of interoperability and why we use reverse engineering. And then of course we can use it for maintenance. If you've got a part that's broken or that you know may fail, how do you go ahead and prevent that? So a few examples. One is in terms of where the documentation exists, but it's not necessarily available to everyone. So think about your cell phones or your game consoles or even some of your computers. Someone, service maintenance people, companies have documentation on how to repair a product, but that doesn't necessarily mean that you have access to that documentation. So that's where companies like iFixit will get a new product as quickly as they can, and they will have a team of people that go ahead and figure out how to take it apart, what parts do they need, what parts does it have, how do they piece it together, and then they'll go ahead and come up with documentation that's freely available so you can go ahead and repair your own iPhone, or you could swap out the battery on a laptop that for some reason is difficult to get to. So there's a video on YouTube on how they actually did the tear apart process on one of the iPhones as soon as it came out. But we've also got things like with the COVID-19 and the coronavirus, there's a high demand for ventilators. And some of these pieces of equipment have been in storage for years. And when they're coming out of storage, they're not working. So one company, and this is just one of many examples out there, but Bloom Energy is a fuel cell company out in California, and they have technical skills, they have technical equipment, they know how to analyze what's going on in the system. And while they're not a medical company, they recognized the need, they recognized the skills they had, and they worked with the government in California to go ahead and test and repair the ventilators that needed to be getting out to the hospitals. So they had to reverse engineer some of their own documentation to go ahead and decide how to best approach the problem. Now, we can also use reverse engineering for discovery. Academic, research, learning, it can be for curiosity. Kind of sticking with some of the medical themes, reverse engineering the brain is one of the grand challenges that we've talked about, but how does the brain work? How does it function? And in the case of people that need things like prosthetics, for a long time, it's been just a fixed attachment, a hook, or a basic, appearance of replacing a missing limb from an injury. But as technology's gotten better, technology's gotten smarter, we have robotic arms. But how do you actually have the brain connect to that more traditional electronics? Okay? And that's where we've been using reverse engineering the brain to go ahead and work on that. And the military, the U.S. Army, has done some really cool research in that regard. Another great example of reverse engineering is the Human Genome Project. And this was a project where trying to figure out how DNA works, what's it actually mean. And while there's still a lot of research still going into that, it took 13 years before we were able to go ahead and sequence the genome. But now that we have, and we've developed better and faster tools for doing that, kits like 23andMe or what Ancestry's done, it will go ahead, sequence your genome, and it will give you an idea of where did you come from, what countries and ethnicities maybe you originally had, or it can start to give some clues to what medical conditions you might have. And that raises a lot of questions of ethics and best practices, but it's something to kind of consider, that now you can know your own genome and you can use that to make decisions about how you live or what treatments, conditions that you may have. Now, the other place of where reverse engineering is used in terms of discovery is in military and commercial intelligence. This is a great example of kind of how the tools and the machines, the weaponry that we create for our armed forces is copied by other countries. So one example is a more historical one. So in the World War II, the B-29 was a bomber that the U.S. was using around the world. And unfortunately, in war, these things will be shot down, or they'll have to make emergency landings and not necessarily be given back to the U.S. government. So even though Russia was neutral in terms of what was going on between Germany and Japan and pretty much everyone else, they got access to 3 of the B-29s. And what they did was they reverse engineered them. They used one for flight tests and training. They used a second one as a reference. They kept it fully assembled and operational. But a third one, they went ahead and fully disassembled it, and they copied it exactly. And they did their best to go ahead and make the Tu-4s their own version with the materials they had. And the downside is they had to adapt to some of the resources they had that they couldn't quite match up what we had. So they ended up with a plane that weighed 3,000 pounds more, but small defects that were in the one that they took apart were copied almost to the exact location. Now, more recently, we have things like the RQ-170, which was a drone over Iraq, and what happened was it crashed. Okay, it was forced down, and they were able to go ahead and start analyzing a lot of stuff on a project that had been very top secret at the time. Okay? So whether it's military or even in commercial cases, there's a lot of opportunities in reverse engineering what someone else has produced and seeing what you can do with that information. Now, there are also cases where it's kind of after the fact. So rather than direct competition at the exact same time, when things fail, we need to know why. So in the images on the bottom of the screen, we're seeing a case of a walkway that collapsed in the Hyatt Regency in Kansas City. And this is a very famous case where they weren't sure if it was people not paying attention to instructions and they had too many on the walkway. Was it a failure of the people that built it, or was it a failure of the engineers who designed it? And what they had to do is they sent in engineers to go ahead and analyze and test the materials. Maybe it was bad materials that caused the failure, maybe it was other things. Okay, so they actually discovered that the design had been correct, the engineers did the right things, but the way that it was assembled, the way that they actually built it, the contractors that were building the building took some shortcuts. And what happened is we had a lot of people die, a lot more that were injured. And it's unfortunate, but it's something that still happens in today's life. So there are a form of engineers who are forensic scientists, who basically determine how something failed. Now, there are other cases where if there's patent infringement, or if it's a concern of was it copied and there were protections in place, there are other cases, but there's definitely a form of reverse engineering that looks into those cases. The final kind of case for reverse engineering is being able to use that to improve or redesign a product. It could be making it more efficient, making it more reliable. Think about the iterations that go through in normal designs. A company will reverse engineer their own products to see what went wrong, to see how they can make it better. We can also see it used for improving manufacturing techniques. We can use it to eliminate failure modes. We can use it to reduce cost. So some of the reverse engineering going on with ventilators right now is actually going back and looking at versions that came out in the 50s and 60s, but how can we use modern technologies like 3D printing or laser cutting to make the same products at a lower cost at a faster pace. We can use it to increase ease of use. How does a piece of technology become more useful? How does it become more functional? We can also use it to become a greener product, less damage to the environment. And we can see how we can reuse parts. There's a lot of effort right now that because there's a limited supply of the minerals, the metals that we use in a lot of our high-tech devices, how can we go ahead and recover that from products that have already been processed? So in terms of reverse engineering tools, and how do we actually go around investigating those different products, there's a lot of different tools. Some of them are going to vary depending on what you're trying to analyze. But a good starting point, at least where we are concerned, are calipers, which we've come to use in class, and we know that we can get down to 10,000ths of an inch precision. Micrometers, a very similar tool that offers even higher level of precision, usually used for thicknesses of metals or thinner materials. Sometimes we have trouble getting a measurement of curvature, the bevel that goes onto an edge. And that's where we can use things like radius gauges or other pre-manufactured models. But there's also more advancements in imagery. So optical probes and microscopic cameras can be used to go ahead and investigate inside of a product. Things like medical imaging, so x-rays, CAT scans, MRIs, are not just for medical purposes, but they can also be used to see inside an object. We've got newer technologies like 3D scanners and photogeometry, where taking enough photos from different angles and different positions can help us get a better idea of the geometry of a object that we are imaging. So some of those are getting to become apps on your phone, while other things will remain more costly and more difficult to get to. But there's a lot of value in understanding some of these tools for when you need to analyze an object. So the basic process for reverse engineering. This is not something we're going to really focus on doing in class as an assignment, but it's a good understanding, it's a good baseline, because reverse engineering is something done in principles of engineering. Those that go on to the engineering design and development class, you're going to have to look at other products to see what you can make improvements on. But the basic stages come across as visual analysis, what do you see on the outside, functional analysis, so how does it work, and then you get into some of the structural analysis where you start looking more at the internal structures and how it works. So functional analysis starts with the product being selected, and ideally you're using a non-destructive approach to it. Okay? You're not trying to break it yet, you're not doing anything that's going to permanently damage it. You're just basically seeing what is visible from the outside. And you're using that to go ahead and help identify the purpose. What is it supposed to do? What the problem is it there to fix? From there, your observations are allowing you to determine the functions. So what is it that it actually does? Not what problem is it solving, but what steps does it do to go ahead and solve that. And then you get into the inputs and outputs. What do you have to contribute to the system before it's coming up with features, the functions, that are going to be more useful to you? So, what's the purpose of this? Well, we know that the purpose of a toothbrush is to clean our teeth and gums. It's there to prevent tooth and gum decay. But we know that we have to use some water and some sort of cleaning paste, whether it's baking soda or if it's an actual toothpaste. But used in conjunction with the brush, it's actually taking away the plaque and the other things that we want off of our teeth. So, in terms of an electric toothbrush, this is where we start looking at the functionality of it. So, using an annotated sketch, we can see things like the head will rotate, okay? There's a vibration going on. There's some way for it to go ahead and provide that rotation, so we know somewhere in there there's a motor. But the housing that covers everything is to help make it waterproof. But at the same point, there's a soft grip to allow us to go ahead and control the directionality of it. And then there are switches, usually just one to go ahead and determine power, but maybe you've got an indicator. That's only what you're seeing from the outside. More destructive processes would start actually taking it apart. So you would see how the head attaches to the body, what type of battery is held inside, what sort of electronics are inside. You might do more to determine what materials are used. Okay? But the whole concept here revolves around what is called the black box systems model. It's not that important for you to understand what's going on inside the product. It's recognizing what are you contributing to it. So what are you putting into it? You're lifting and holding it. You're moving it around your teeth for you. You are, what is it that you are doing? And then what is the system's output? Okay? We press this switch, the head starts rotating. The head starts rotating for so long before it may give you an alert saying you've been brushing your teeth for 2 minutes. So just re-emphasizing this, the black box is used to go ahead and represent where you're going from the internal components and processes to what's going on the outside. Okay? So it's knowing that there's a difference between those. So going back to the example with the toothbrush, okay? Your hand motion controlling the toothbrush, the toothpaste, the water, and some sort of energy, the electricity that's being provided for it, whether it's charging or if it's a disposable alkaline battery. And then what it creates, okay, as its functionality, is we know that there's going to be a sound with it, whether it's just the motor or maybe it's one that's designed to play some music as you're brushing your teeth. You get some amount of heat. Again, there's heat waste in pretty much any product. You have waste, okay, the toothpaste that's no longer usable. But the desired outcome is you're getting clean teeth and gums. Not all of those are things that are directly attributed to the toothbrush itself, but it's understanding that the combination of your inputs with the brush lead to those outcomes.